Hello guys, I think many of you heard of the term Brownian motion, but nobody actually gives a clear explanation of what that is. They usually just give you a bunch of academic terms and leave you confused, so this video and my free guide will make it a bit more clear what the Brownian motion actually means. Long story short, the Brownian motion is a mathematical way to describe something moving through tiny random nudges, one after another continuously. So think of it like this. Imagine like you're blindfolded and every second someone gives you a small push, left or right, completely randomly, where you end up after 1,000 pushes. That's the Brownian motion. Mathematically it has three properties. The path is continuous, so no teleporting, no gaps. Each move is independent, so the last nudge tells you nothing about the next one. And the uncertainty grows with time. Specifically, it spreads out like a square root of time. In math, standard Brownian motion is also called a wiener process. You start at zero, every change over any time interval is normally distributed, like bell curve. So let me demonstrate that. As you can see, here's our normal distribution, and as steps reveal, it converges to our normal distribution. So let me give a bit more space. You see, the distribution converges to the normal one. The key formula looks like this. The change from time s to time t is normally distributed with mean 0 and variance equal t minus 1. So translation, basically the longer you wait, the more spread out things get, but no matter how much history you have, the next move is still unpredictable. Now pure Brownian motion is just noise. In practice we add two ingredients, drift and volatility. Drift is the average direction, so usually in the stock market everything slightly goes to the upside, so that's our drift. And volatility is how wild the randomness is. Put them together and you get x at time t equals your starting point plus drift times time plus volatility times Brownian noise. This is called arithmetic Brownian motion. It's a cleaner model, but there is a problem. It can go negative. That's fine for some things, but not great for prices. Exception was crude oil around 2020 when it went negative. Now let's talk about GBM, geometric Brownian motion, usually used in all kinds of pricing models. This one you need to know if you're in finance. Instead of adding random noise to the level of price, we apply it to percentage changes, so the price can never go below 0. The formula says the change in price equals drift times current price times dt, so small increment of time, plus volatility times current price times the Brownian shock. This is the model behind Black-Scholes. It gives you log normal prices, meaning log returns are normally distributed. A quick caveat, a GBM is a teaching model, so real markets have jumps, volatility, clustering, fat tails, and GBM doesn't capture all of that, even though it was used in Black-Scholes model. There's a big family of different Brownian motions, and we will talk about Brownian bridge. I found out about it from Roman Palusi. I hope I pronounced his name correctly. So, Brownian bridge. What if you know where the path ends? Brownian bridge. What if you know where the path ends? As you can see, when we resample it, the end at the beginning always remain the same, but we don't know what happens here. You pin both endpoints and let the middle wiggle, typically used when you know the target. And reflected Brownian motion. What if path hits the floor and bounces back, like capital that can't go negative? So as you can see how it looks like. Absorbed Brownian motion is what if hitting the boundary stops the processing of like ruin probability. So once you're broke, you're out, basically hitting a drawdown on your funded account. Fractional Brownian motion. What if moves are not independent? The hurst exponent controls the memory. H above 0.5 means trends persist, H below means reversions dominate. And ornstein uhlenbeck mean reversion process is a Brownian noise, but with a mean reversion pool classic for interest rate spreads, and it's a gravitational back to the center. So imagine there is like a mean and we simply oscillate above and below it. But I have to give you some reality check. You have to ask a couple questions before using it. Can I assume the path has no sudden jumps? Can you assume that the asset returns are normally distributed? A hint you can't. Can I assume each move is independent of the past? And if the answer to all three is roughly yes, great, use it. If not, you need a richer model, and I will go about that in my further videos. Follow the channel to not miss them. So I explained the Brownian motion from the core intuition all the way to the family of models built on top of it. So if you wanna see how to simulate one in Python, I mean, you can open Wikipedia, but I will also make a video about it. So now let's get to the simulator I've built. It's inspired again by Roman. I stole the design kinda from his Gaussian cookbook. But I mean, as you can see, design is still very different. It's just alike, and it took me a lot of effort to create. So there are two completely separate things you choose. First, you pick your target, meaning what structure do you want your random path to have. Second, you pick your recipe, meaning what algorithm are you going to use to actually generate paths that have that structure. So does the recipe actually produce what the target says it should? So the covariance kernel panel, this is the first interactive panel, and it's, as you can see, called target covariance kernel. This sounds technical, but it's just asking how should points in your path be related to each other over time. You get three choices: Brownian, bridge, or fractional. So if you pick Brownian, the kernel is k of s and t equals the minimum of s and t. What it means in plain English is the further apart the two time points are, the less they have in common. But earlier time points are always contained inside later ones, because you got to the later point by passing through the earlier one. That's why the heat map, it shows you like it's bright on a bottom right corner and fading to the left upper one. If you switch to bridge, as you can see, the covariance is 0 at both at endpoints, as it's set here, and largest near the middle. And as you can see how hurst parameter changes here. Let's maximize the resolution. As you can see, the hurst actually shows how the covariance changes. Now let's get to the simulator panel. This is where you actually generate path, and if you pick recipe either continuous time KL or discrete covariance factorization, these two are completely different algorithms for building the same thing. The KL recipe is Carlo, I hope I pronounced the name correctly, builds your Brownian path as the sum of sine waves. Each sine wave gets multiplied by a random normal number, and as you add more terms, you get better and better approximation of the true path. The formula looks intimidating, but the idea is simple. You're decomposing randomness into frequency components, like how a song made of individual notes. Actually, that kind of resembles wavelets, so let's increase KL terms, and as you can see, it more and more resembles the Brownian motion. Here is our error, as you can see, and here you can see the heat maps, and theoretical one, it doesn't change. The discrete recipe works differently. It directly factors the covariant matrix using linear algebra, then multiplies that by a vector of random normals. It's more brute force, but more exact. As you can see, we lose our KL option and we generate our path just like that. In continuous time, KL terms controls how many sine waves components you're summing with one term. The path looks like basically sine waves. And as you increase, it's more converges to the true Brownian motion. Here you can simply preview how each one of them looks like. Again, use or misuse you can read yourself. So here also the sources I added: Gaussian cookbook by Roman, also his recipes for simulating stochastic processes, and there's plenty of material online that universities post on the topic. So I hope you've enjoyed this video. I hope it's finally clear to you what the Brownian motion means, and don't forget to join the Discord. You're free to ask questions there or in the comment section. Please like, subscribe, and until the next time, be safe.